All right, welcome back and thanks for joining us today. If you remember yesterday, I said that in another video I was going to talk about the reason why you might still be able to use the traditional Euclidean uh, geostatistical simulations if you still want to in Antarctica. And basically, over here we will talk about uh, scale issues or maybe scale assumptions because then first, we were talking about the entire ice sheet. And so if you look at the entire ice sheet, of course, talk about the fact that UTM projections can be helped to deal with in Antarctica. So we decided maybe it's just a reasonable choice to decide to go with the simulation in this sphere, right? But imagine now instead of using the entire ice sheet, you just want to process the data within 1 kilometer square, which is what we do when we want to produce time series over the ice sheet. So imagine you pick a location on the ice sheet and you want to see how the surface elevation is changing at that location. You will make a time series of that surface elevation, right? And so if you want to do that, you still might be able to do it using traditional Euclidean simulations. That's what we will discuss today. And so you imagine you have these data within a 1 kilometer square, and it's basically a collection of all those points uh, measured by different missions. I said I said two. I said two in this case because it's Antarctica, and the location where, for example, I would run this example doesn't have any ATM data, or maybe there is ATM, but I couldn't find any. So if you have any ATM data in Antarctica and you want to share, or you have any other altimetry data in Antarctica that you feel like you want to share, maybe it's something that you collected by your own means. If you feel like you can share it and it can help, please do. I will be happy to, um, connect with you and try to work that out. So basically, um, you need, like I said, you need those data. Of course, it's the format depends on you and also the tool that you're using. But most of the time, for that size, a CSV will work. And when I plot them here, you can see I have surface elevations over here, but you can see we have some extreme values, right? So always kind of look at the data and see if you can do any sort of cleaning before you run your model. But the reason why I'm doing this is just to show you that when I use the traditional Euclidean simulations, I'm still able to get out with a decent result. And so that's the idea behind this. So you have the data, you go and make uh, subsampling button for some cleaning, and you want to clean the eyesight 2 data. I hope this one is not one of those data sets where I flipped. I was working testing these things and I made a mistake. I flipped eyesight and eyesight 2. Eyesight was eyesight 2 and eyesight 2 was eyesight. So this step is to de-densify eyesight 2. Eyesight 2 is a very good data set in terms of redundancy. You have points very close to each other. And for time series modeling, maybe you don't want that much information. So for one track, you can decide, okay, I'm going to skip maybe each 10 meters and pick one point on that track and use my subsample or my resample. Yeah, I think it's better to call it a resampling. I will pick the new sample and work with it instead of the initial pretty dense track. So to do it, I just select the sensor I want to work on, and I say, okay, do not just pick randomly when you have the data set, right? Look at one track because most of the time those are collected at the same time. Look at one track collected at the time t, and on that track only remove the points that you want to remove given the algorithm that you're implementing. And so you run it. And speaking, I don't know if you were able to see it, but those are like, you have the blue, you have the blue, those are the original data, and then the red one are those that you will select. So over those, you can see they were like pretty close to each other. You will skip some to pick the red points. When we're done with it, you now can remove that extreme value. So to remove the extreme value, two things. You can look at this plot and just directly identify what is extreme. Like I can see this is 500, so this is going to be 600. And they are all between 500 and 600, maybe except uh, for this line over here. But I can survive missing a few here, so I would say it's between 500 and 550 or 6. Okay, let's just be loose and say 500, 600. And when you cut, if you plot this again, you have something different. So now you remove the extreme values. All you have now is the remaining data. So again, this is really, I should be able to plot the 3D just to show you. Yes, thank God it didn't crash. I was checking last time and I think we had an issue with it. Yeah. So this is like a 3D distribution of all those points. I have three, so that's why we see three colors here. We have ISAT 2 and CROSAT 2, so those are like the green, blue, and black dots. Most likely the blue and black are ISAT and ISAT 2, and the green one are probably CROSAT 2 because they are less structured compared to ISAT and ISAT 2 in terms of, following a track kind of thing. But this is just to show you this is a 1 kilometer square patch, and the data are collected in space and time for its sake. It's a space-time domain. So now what we will do here is we will simply use Euclidean simulations here. So like simulations in an Euclidean space, not in sphere. And you will see we still can have some decent result. First step, as always, this is variogram based geostatistic. It's not multi-point, it's just 2 point. And first step, you need to compute a variogram model. And remember, this is a space-time domain. So this program is not just like there is a good conversation here, right? Because most of the time when people are doing special temporal program models, what they do is they want to have a component for space and a component for time. I don't like that idea. I like to think that the program was defined as a structural function, which is a function of one variable, h, and h measure the lag distance between 2 points uh, in any given domain. Could be space, could be time, could be space time. And so if you have space time, you need to find a way to compute the distance between 2 points in a space time. If it's space, then it's fine. And again, remember, we are using Euclidean distances here, so Euclidean norms, so should be like the r square plus z square, the entire thing in the square root, and then you have your distance. Oh, right, but this is when you use the circle. So it's x squared plus y squared plus z squared, the entire thing, in the um, in the square root. So anyway, we are here and we have a model. Something I want to point here before we move forward. Very interesting, and it is. Of course, you can use. I don't know. Someone will say, "Well, I can use a Gaussian model to fit this, or I can use an exponential model to fit this." But what I see here is none of these. But it's basically like a sine function that is attenuating itself over the time, and then after some point you have like something that you will neglect because, of course, we know that at some point normally we want to get closer to the variance of our data set, so we will neglect some part of it, right? But I am more interested in this shape over here, which means most likely this is if I am very good in doing this covariance function modeling, I will probably end up using something which has like which is close to like a sine function or cosine function, those type of functions. So I have this because this is a function that we are not really talking too much about, but it is very useful, I feel, especially in this type of field where you deal with data like, uh, for example, for ice sheet, you have seasons where you have precipitation coming. During those seasons, you expect to have a bit of ice accumulating over the ice sheet, and you have summer where it is very hot, and you expect to have some ice melting on top. So you expect to have some uh, um, surface elevation is going down, right? And so it's going to repeat next year. So whenever you have this type of repeated pattern, I'm feeling like we need something like this, something like sine cardinal functions. Those are normally capable of capturing those repeated patterns and help you integrating those into your simulation process. That's why I'm picking this. And of course, if you have more to add into this topic, feel free to jump into the comment section and add your thought or maybe your own experience of using it. I would love to hear about those. So always you need to specify the range, which is great. Uh, uh, I need to specify the seal, which in this case I'm not sure if it's a real seal. I will have to double check again because I know some covariance models will have a real seal, like the spherical model have a real seal, but the exponential and the Gaussian one they don't have a real seal. It's like a practical seal, but it's not real because those functions are not really um, converging to a point when you go to the infinity. It's always growing when you go to the infinity. It's growing, but it's not growing as fast as when you're closer to the origin. So that's why we call it practical seal. But enough of detail about those. Let's just move and put the value here. Let's go and say 2 just to see how it works. I just want to show you that even with the Euclidean or Cartesian traditional simulation, we can still have some decent results. So now you see the range is a little bit off and the seal also is a little bit off. So I'm going to push it back a little bit. I can do it by decreasing the range here, 1.5. And maybe 2 is too much, right? Maybe, oh no, 1.8. So that's coming, okay. Looks decent. So maybe 1.5 is too much as well. And remember, the range is usually the distance in which you can observe a sort of domain related correlation. So it's a correlation between the observation based on how close they are to each other in a way. It's like we used to say it's like a spatial correlation. No, it's the length or the yeah, the distance through which you observe spatial correlation among observations. So it helps you understanding the range in which you can believe observations are kind of in maybe not explicitly or implicitly, but are kind of in a very complex way, I would say, because it's hard to kind of describe this one, but they are like interacting with each other, not interacting in terms of, oh, they're touching each other, but like if you move one, probably that is going to impact the values of the surrounding observations. An example, I take a cup of tea, I'll put one sugar in the middle of it. After some time, it's going to diffuse and change the taste of the fluid around, right? Not exactly the same thing, but this is what I was trying to explain here. Like this is the distance where you can think of removing or changing a value, and it might have an impact on the surrounding observations. That's how I used to understand this. So we thought, and now it's another thing that is very important here is These type of random functions, I personally would expect them to be extremely heterogeneous in a sense that when I model this diagram, I am always tempted to say I have something like two different models working here. I just can't prove it mathematically yet, but I'm working on it. Okay, so for now, I will just use this as it is right now, just to show you the result, and you'll see it's not crazy. It's not too bad to think that it's not a good idea to use Euclidean traditional simulations here. So this is my model, right? I can stop there, and what I want to do now is to produce the time series that is going to represent this data. So very simple. I have the, oh my god, I hope I remember the one that is ready to use. I think it's this one. Uh, I'm working on it, and progressively I'm changing different buttons. I'm coding the background functions. I think they call it callback. And sometime when you spend maybe 1 month not working on a project like this, my document on this one is just so bad that even when I read that document, I'm not proud of saying it is bad. But when I read that document, sometimes I'm lost. So it's not always easy for me to kind of. That's why I like to keep these things just to, with this record, for example, I know now that this button is exactly doing what my mind thinks it's doing, and I can tell you what it's doing. It's doing is sequential regression simulation. Bayesian-based sequential regression simulation is something that I'm trying to push out there so that people start using it more and more now. But yeah, we're ready, and I can show you what we have. Let me just fix this. Okay. And I remember we were using 500 and 600. I'm pretty sure 500 and 600 is not a good quality. I can see here. So when you look at the plot here, 500 and 600 is a bit too much. So maybe I'll say 500, 535 to see what we have. Okay. It's not that bad. We still can improve a lot, but it's not bad. I can go down to 505. I mean, up, sorry. And also, yeah, I can go 525. Okay, I can stop there. Still not easy to read the graph, sorry for that, but we can fix it. Change the colors just so that we can see exactly what we are dealing with. Okay. Okay, that's ISAT. Let me change ISAT to as well. We will give them a. I'll give them the same shape but just different colors so that we can navigate through the graph without really struggling with. Yeah, it's better. I can already see the trend of my time series. But let's go and change cursor to as well. Love it. I love it. I love it. Using dot will also be a good idea if you see what I mean. But I don't know. Sometimes I just like to use square for the input so that they are like they can capture your attention pretty fast because they usually give you an idea of what the time series should look like. If you use dots, it's going to be hard for you to read on the graph and have that idea. But right now, when I look at the graph, normally I have the ability to guess how the time series will look like. Maybe I don't want to change the color of this. No, let's change it. Let's use a blue color like this. Like anyway, blue. Perfect. So now my model itself. I'm using a line here. I've used that just to make sure I can see through it. Perfect. This way. And the uncertainty, very important. Okay. If that's and the reason why I have these two is because want to be able to plot this right. So you see, this is the graph. So like I said, oh, well, we have these. I don't like it. I don't like it. Well, it's caused by cross-net 2. Cross-net 2 is really hard to deal with. I can tell you right now. You never know what to expect with cross-net 2. Over here, you see it's good, but here it is just giving me this. I can always add something which is like outlier detection and outlier removal, and this might be an outlier that I would take because of the way it is evolving here and remove it. Or this is really what happened at this location, and I just don't know. Like I'm trying to remove something true, right? So, but anyway, I wanted to show you this because I wanted to show you how you can still have a good result even if you're using Euclidean simulation of intrinsic random function in the sphere. So you still have, depending on the scale in which you're working, you still have that option if you like to use it. But remember, it's a scale question. How large is your domain? How big is it? Do you think you can do those projections, a UTM projection, and have your XY coordinates and use this without any struggle? If you can, that is fine. If you cannot, just use simulation in the sphere and you still have results that you can interpret. And most of the time, it is the same challenge, nothing very different, same challenge. So, yeah. Uh, like I said last time, now we will have to talk about the Greenland case in another video, not now. But this one also I said and I did. So, wait for the Greenland case. Until then, see you.